Welcome back to AI Paper Podcasts. Usually we're dissecting the latest cutting-edge research, but today we're taking a trip back in time to revisit a true classic. Playing Atari with deep reinforcement learning from way back in 2013.
Oh, wow.
I know ancient history, right?
Yeah.
But in the world of AI, this paper was a total game changer.
It was.
It basically kicked open the doors for all the amazing things we're seeing today with AI playing games. So we're going to unpack why it was such a big deal.
I think it's fascinating to look back at papers like this because you can see how the seeds of current AI were planted almost a decade ago. This paper was truly visionary in how it tackled a problem that had stumped researchers for ages. How to get a computer to play games using only the visual input, just like a human would.
Exactly. Back then, most game-playing AI relied on hand-coded rules or some knowledge of the game's mechanics.
Right.
But this paper was like, let's just throw the AI in the deep end and see if it can swim and swim it to do it.
And it wasn't just doggy paddling either. This paper introduced the Deep Q network, or DQN, a neural network that could learn to play Atari games at a superhuman level just by looking at the screen. That was a massive leap forward, showing that deep learning could be applied to complex control tasks with just raw visual data.
Think about that for a second. No cheat codes, no rule books, just pixels on a screen.
Wow.
And from that, the AI learns to play the game, often better than humans. It's like teaching someone to play chess just by showing them the board and letting them figure out the moves.
And that brings us to another key insight: experience replay. Just like a gamer reviewing their best and worst moves, the DQN stores its experiences and then randomly revisits them to learn more effectively. This helps stabilize the learning process and prevented the AI from getting stuck in a rut, always repeating the same mistakes.
This whole paper is a goldmine of clever tricks. But the biggest takeaway, the one that truly sent shockwaves through the AI community, was the results. DQN wasn't just good. It was often superhuman. It achieved top-level performance on 3 of the 7 Atari games it was tested on, and outperformed other learning methods on all 7.
And this was all the way back in 2013, when deep learning was still in its early days. This paper showed the world that deep reinforcement learning was a force to be reckoned with, and paved the way for breakthroughs like AlphaGo and all the incredible AI-powered robots we see today. So for those of you keeping score at home, that's the 1-minute highlight reel of why this paper is a landmark achievement.
Now, for those of you ready to take the full deep dive, let's get into the nitty-gritty of reinforcement learning and why using it with raw visual data from video games was such a challenge.
So imagine you're an AI agent dropped into an Atari game. You can see the screen, but you have no idea what the controls do or what the goal of the game is. All you get is a score that goes up or down based on your actions. Your job is to figure out how to maximize that score over time. That, in essence, is reinforcement learning.
It's like being airdropped into a foreign country with no guidebook and just a vague sense that you should probably try to earn some local currency.
Exactly. Now, doing that with raw sensory data like video presents some unique hurdles. First, you're dealing with massive amounts of information. Each frame of an Atari game is a grid of pixels, and those pixels change rapidly. Trying to make sense of all that data is like drinking from a fire hose.
Okay, I can see how that's a problem. High dimensionality. What else makes this so tricky?
Another challenge is that rewards in games are often sparse and delayed. You might make a series of seemingly good moves, but only get a reward after achieving a specific goal, like completing a level or defeating an enemy.
It's like investing in the stock market. You might make a bunch of trades, but you don't know if your strategy is actually working until much later.
And then there's the issue of non-stationary data distribution. As the AI learns, its actions change the game state, which means the data it sees also changes. It's a constantly shifting landscape.
So it's not just learning a static set of rules, it's learning in a dynamic, ever-changing environment.
Precisely. And that's why this paper was such a breakthrough. It introduced a way to tackle all these challenges using a single, elegant architecture, the Deep Q network.
All right, let's break down this DQN. First, the deep part. It's using a convolutional neural network. Now, for our viewers who might not be deep learning gurus, can you give us a quick, intuitive explanation of how those work?
Think of it like this. When you look at an image, your brain doesn't process every single pixel individually. It looks for patterns, like edges, shapes, and textures. Convolutional neural networks do something similar. They have layers that act like filters, detecting these key features in the visual data.
So it's like the network is learning to see the game in a way that's relevant to playing it well.
Exactly. And the Q in DQN refers to Q learning, a classic reinforcement learning technique that helps the network estimate the long-term value of its actions.
Okay, so the DQN can handle the high dimensionality and figure out the long-term consequences of actions. But what about that shifting data distribution we talked about? How does it deal with that constantly changing environment?
That's where experience replay comes in, instead of learning just from the most recent experience. The DQN stores its experiences in a memory bank and then revisits them randomly during training.
So it's constantly learning and relearning from both its successes and failures. It's like a basketball player watching game replays to analyze their moves, right?
That's a great analogy. And this random sampling from past experiences helps break the correlations between consecutive game states, which makes the learning process much more stable and efficient.
That's like learning from a shuffled deck of flashcards.
Yeah.
Instead of just going through them in order, you get a much more well-rounded understanding that way. Okay, so we've got this powerful neural network architecture with a clever learning strategy. But let's get down to brass tacks. How did they actually train this thing? And what games did they use to put it through its paces?
They tested DQN on 7 classic Atari games: Beam Rider, Breakout, Enduro, Pong, Qbert, Sequest, and Space Invaders.
Right.
Each game presents unique challenges, but they use the same network architecture and hyperparameters for all of them.
Wait, so no special tweaks or customizations for each game? That's pretty impressive. But didn't we say that Atari games have tons of visual detail? How did they manage to train this thing efficiently?
They did a few things to make the training more manageable. First, they pre-processed the raw pixel data, converting the color images to grayscale, downsampling them, and cropping them to focus on the core playing area.
So they basically slimmed down the data without losing the crucial information the AI needed to play the game.
Exactly. And they also used a technique called frame skipping, where the AI only had to select an action every 4th frame, repeating the last action on the skipped frames. This significantly sped up training, because running the Atari emulator forward is much faster than having the AI make a decision every single frame.
Clever. So they made the data lighter and slowed down the game's internal clock without compromising the learning process. Any other tricks up their sleeve?
One more important detail was reward clipping. They capped all positive rewards at 1, and all negative rewards at Medic 1.
Hold on. Wouldn't that make it harder for the AI to distinguish between, say, a small reward and a big reward? Why would they do that?
It's a trade-off, but a smart one. Different Atari games have wildly different scoring systems. By clipping the rewards, they created a more consistent learning environment across all the games, allowing them to use the same learning rate and parameters for all 7.
Ah, I see. So it's like creating a standardized grading scale across different classes. You lose some granularity, but it makes the overall evaluation process more fair and consistent. So we've got the architecture, the learning strategy, and the training techniques. Now let's get to the moment of truth. The results. Spill the beans. How did DQN actually perform? Did it live up to the hype?
It surpassed the hype. DQN significantly outperformed all other learning methods they compared it to on all 7 games.
Wow.
And here's the kicker. It even achieved superhuman performance on Breakout, Enduro, and Palm.
Whoa, superhuman performance. That means it was consistently beating even the best human players. That's wild.
It really is. And what's even more fascinating is that it achieved this level of performance just by learning from the raw pixel data. Without any prior knowledge of the game rules or strategies, it was literally figuring things out on its own.
Okay, but let's be real. There had to be some games where it struggled.
Right.
Atari games can be pretty challenging even for humans.
You're right. While DQN dominated on some games, there were a few where it didn't quite reach human-level performance, like Sequest and Space Invaders.
Why was that? Were those games just inherently harder for the AI to crack?
In a way, yes. Those games require more long-term planning and strategic thinking. It's not just about reacting to what's happening on the screen right now, but about anticipating future events, managing resources, and making decisions that have consequences many steps down the line.
So it's like the difference between playing a fast-paced action game like Breakout, where you're constantly reacting, versus a strategy game like chess, where you have to think several moves ahead.
Precisely. And that's where things get even more interesting. The researchers actually visualized the value function that DQN learned, which gives us some insights into how it was making decisions. It turns out that in games like Sequest, DQN was able to learn how the value of a game state changed based on events happening on the screen.
Wait, so it's not just mindlessly reacting to pixels. It's actually developing an understanding of the game's mechanics.
Yeah.
And how different actions influence the game's state. That's kind of mind-blowing.
It really is. For example, in Sequest, they observed that the predicted value would jump up when an enemy submarine appeared.
Makes sense, right? An enemy submarine is a threat. So the game state becomes more precarious.
Definitely. It's like your danger sense tingling when you see an enemy approaching in a video game.
And so the AI is essentially learning to recognize and evaluate threats.
Exactly. And then as the player fired a torpedo at the enemy, the predicted value would peak right before the torpedo hit its target.
Because that's when the AI is about to score points and eliminate the threat, which is a highly valuable state to be in.
Right. And after the enemy submarine was destroyed, the value would drop back down to its original level.
So the AI is not just understanding individual game elements, it's actually learning the flow of the game, the cause and effect relationships between actions and outcomes. It's like it's developing its own gamer intuition.
And that's one of the most remarkable things about this paper. It wasn't just about creating an AI that could win at Atari games. It was about demonstrating that deep learning could be successfully applied to the challenging field of reinforcement learning, opening up a whole new avenue of research and possibilities.
And this was all the way back in 2013, remember? Deep learning was still relatively new then. This paper was like a beacon showing the world what might be possible with this powerful technology.
Exactly. It inspired a wave of research in deep reinforcement learning. Researchers started applying DQN and similar approaches to all sorts of complex tasks, from robotics to natural language processing. And one of the most famous examples of this is AlphaGo, the AI that defeated a world champion Go player.
AlphaGo. That was a monumental achievement. And it was also based on deep reinforcement learning, wasn't it?
Absolutely. AlphaGo used a similar approach to DQN, but with even more advanced techniques, it was able to learn the incredibly complex game of Go, which was once thought to be beyond the reach of AI, at least for many years to come.
So the legacy of this 2013 paper is immense. It wasn't just about playing games, it was about pushing the boundaries of what AI could achieve and laying the foundation for some of the most impressive AI breakthroughs we've seen in recent years.
And that's why it's so fascinating to revisit this paper now. It's like looking back at the roots of a giant tree and marveling at how much it has grown and branched out.
Speaking of branching out, I'm curious to see how DQN actually stacked up against human players. Where did it excel and where did it still fall short? Let's dig into that comparison.
Well, the researchers actually pitted DQN against a professional human Atari player. It was like a classic human versus machine showdown. And the results were really revealing.
Okay, I'm on the edge of my seat. Give me the play-by-play. Who emerged victorious?
It wasn't a clear-cut victory for either side, which I think is actually more interesting. On Breakout Enduro and Pong, DQN consistently outscored the human player, sometimes by a huge margin.
So in those games, the AI was the undisputed champ? What about the other games? The ones that required more strategy and long-term planning?
That's where the human player still held the advantage. In Beam Rider, DQN came close to human-level performance, but didn't quite surpass it. And in Qbert Sequest and Space Invaders, the human player was still way ahead.
So it seems like DQN was better at games that required fast reflexes and quick decision-making.
Yeah.
But still struggled with games that demanded more strategic depth and planning. Almost like it excelled at tactics, but not so much at strategy.
That's a great way to put it. And if you look closely at the games where DQN excelled, they tend to have a few things in common. They're generally fast-paced, the rewards are more frequent and immediate, and they have a more limited set of possible actions.
Yeah, that makes sense. Take Breakout, for example. Every time you hit a brick, you get points. That immediate feedback probably makes it easier for the AI to learn.
Exactly. And in Breakout, you can only move the paddle left or right, so the AI doesn't have to search through a huge space of possibilities, which simplifies the learning process.
Now contrast that with a game like Sequest. There are more actions to choose from. The rewards are often delayed. And there's a lot of hidden information and randomness to deal with. You have to anticipate enemy movements, manage your resources, and make decisions that might not pay off for a while. No wonder DQN had a harder time with that.
Absolutely. Those more strategic games require a different kind of intelligence, one that involves planning, prediction, and risk assessment. And that's where things get really interesting for future research in AI. How do we build AI systems that can not only master tactics, but also strategy?
That's a great question. And this paper, even though it's from 2013, provides some important clues. The fact that DQN could learn to evaluate game states and anticipate future rewards suggests that deep reinforcement learning has the potential to go beyond just reactive decision-making.
Exactly. And remember, DQN used relatively simple convolutional neural networks by today's standards. Imagine what we could achieve with more advanced architectures like transformers or generative adversarial networks. The possibilities are truly mind-boggling.
It makes you wonder what the future holds for AI in gaming and beyond. We've gone from AI struggling to play simple games to AI mastering complex games like Go and StarCraft. What's next? AI designing its own games, AI competing in esports tournaments. I, for one, can't wait to find out.
Me neither. And the journey started with papers like this one, playing Atari with deep reinforcement learning. It was a pivotal moment that demonstrated the power of deep learning for solving complex control tasks and paved the way for the incredible progress we're seeing today.
So if you're interested in AI,
Yeah.
especially if you're working in reinforcement learning or game AI, I highly recommend going back and reading this paper, even though it's almost a decade old. The ideas and techniques are still relevant and inspiring.
And who knows, maybe it'll spark an idea for the next big breakthrough in AI.
Well, that's all the time we have for today's deep dive. A huge thank you to our expert for breaking down this fascinating research.
It was my pleasure. Always exciting to revisit the classics.
And to all of you watching, thank you for joining us on this journey back in time. We hope you learned something new, and maybe even got a little inspired. Be sure to subscribe to our channel for more deep dives into the world of AI research, and let us know in the comments what papers you'd like us to cover next.
Until then, keep learning, keep exploring, and keep pushing the boundaries of what's possible.
Game on.